We're going to be looking at Chapter 2 problems. With Chapter 2, we're going to start by focusing on the velocity problems. So we're going to look at the zero initial velocity and the non-zero initial velocity equations on your equation sheet. What I have written off to the right here are the zero initial velocity equations, because those are the types of word problems we're going to look at first. When approaching a word problem, we always want to try to approach it the same way. We first, of course, want to read the problem, figure out which pieces of information are going to be useful. We will then convert if necessary, making sure to assign all the numbers present in the equation with a variable. Once we've done that, we can then pick what equation is going to be most useful for us and solve. So let's look at the problem. You get in a parked car and accelerate to 35 miles per hour. So that's going to be a useful piece of information in 4.2 seconds. It wants us to calculate the rate of acceleration and the distance. Right, so I'm going to start by labeling the pieces of information and assigning those to a variable. So I have 35 miles per hour. What is that? Is that a distance? Is that an average velocity, a time, a regular velocity, an acceleration? What piece of information is that? Well, it's actually a velocity. I know it says you get in a car and you accelerate to 35 miles per hour. This is not an acceleration though. This is a velocity. I know that because of the units. The units are miles per hour, and we measure velocity, which is similar to speed. One's a vector quantity, one's a scalar quantity. We measure velocity in miles per hour, or in our case, in this course, we want it in meters per second when we plug it into these equations. So this 35 miles per hour, that's going to be my velocity. Next, I see 4.2 seconds. So 4.2 seconds is a time, so I'm going to label that with a T. Next it says, calculate the rate of acceleration and the distance covered. So what it's asking us to solve for is the acceleration, which is represented by the variable a, and the distance, which is represented by the variable d. So once you have your knowns and unknowns listed, you move on to the next step, which is convert if necessary. So in order to use any of these values in these equations, they need to be in a specific unit. So distance, for instance, if we're going to put distance in any of these equations, it needs to be in meters. For velocity, it has to be in meters per second. Now, we don't have it in meters per second, so we're going to need to convert that. So I'm going to take my 35 miles per hour and I'm going to convert it to meters per second. And we have a conversion factor on your equation sheet that will do that for us in one step. And that conversion factor is 1 mile per hour is equal to 0.447 meters per second. So I'm going to set this up just like we did conversions in Chapter 1. I'm going to do my railroad tracks. I'm going to start with the number I'm trying to convert, which is 35 miles per hour. I'm going to then take this conversion factor and put it here. I want to put it so that the miles per hour portion is on the bottom in the denominator, and the meters per second portion is on the top in the numerator. This allows for the units of miles per hour to cancel since they're on opposite sides of the horizontal line. So to solve, I'm going to be multiplying 35 times 0.447. When I do that, what I get is 15.645 meters per second. Notice I am not counting significant figures, because this isn't my final answer. I don't want to round to the appropriate amount of sig figs until I'm reporting my final answer. Until then, I want to keep as many digits as I can to get a more accurate final answer. So I'm going to go ahead and erase this top portion. I'm going to fill in the meter per second version of velocity here. So 15.645 meters per second. Okay, so now I have converted. Then let's look at our next variable, time. Time in seconds. Is seconds what we want time to be in? Yes, it is, so we don't need to convert that guy. Now, acceleration is one of the variables we need to solve for. And whenever we're using these equations, when we solve for acceleration, the units are going to be meters per second squared. And we just said a moment ago for distance, the units will be meters. So now let's find the appropriate equations. Since we have two unknowns, acceleration and distance, we're going to need two different equations to solve. So how do you pick what equation is going to work? Well, let's say we're going to solve for acceleration first. So I'm going to solve for acceleration. So what I want to do when I'm looking at these equations is I want to find an equation that has velocity, time, and acceleration in it. So as I go down here, you'll notice there are two possible options. This equation has velocity, acceleration, and time, and this equation has velocity, acceleration, and time. Now these are actually the same equation, just rearranged. The one I'm going to choose to use is going to be this guy here, because that way I don't have to rearrange the equation at all. It's already rearranged in the way that I would like it. So now I just need to plug in my values, and I'm going to make sure that I use the meter per second version of the velocity. So 15.645 meters per second. I'm going to divide that by the time, 4.2 seconds. And when I divide that out, I get 3.725 on my calculator, and the units are meters per second squared. So these seconds don't cancel because they're both in the denominator, because that's a per second. So instead, it's like taking seconds times seconds, which makes seconds squared. And that's good because notice it matches with the units that should be for acceleration. Now, since this is one of my final answers, I want to go ahead and look at my significant figures. So when I'm looking at sig figs, I look at the original two numbers in the word problem itself. I'm dividing, so I'm counting total sig figs. So I have two significant figures in the velocity amount, and I also have two significant figures in my time amount. So that means I should have two significant figures for my answer. So 1, 2, look at the number next to it, that stays a 7. So 3.7 meters per second squared would be the correct acceleration of that vehicle. I'm going to erase this and make room to solve for the next variable. So next we're going to solve for d, distance. So now we know velocity, time, and acceleration. So when we're solving for distance, we can find an equation with all four of those variables. Okay, so if I look through, so the first one has distance and it has time, but it has average velocity. We don't have average velocity. That's why that equation won't work. The only other equation with a d in it is this bottom guy here. And that one will work because we have acceleration, we just calculated it. And we also have time. It was given to us in the problem. So this is the equation I would like to use. Now I'm just going to fill in the variables and solve. So I have 1/2, A is 3.7, time was 4.2 seconds. Let me include the units so you can see how they cancel quick here. So 3.7 meters per second squared, and then time was 4.2 seconds, and we're squaring that. So notice we're going to have seconds squared, and once we square this, we'll have seconds squared there as well. So those will cancel, because this Let me rewrite it so you can see it better. Meters per second squared. The second squared in acceleration is in the denominator, and this second squared will be in the numerator. So they'll be on opposite sides of that horizontal line, thus canceling each other out. So let's enter this into our calculator now. So we get 1/2 times 3.7 times 4.2 squared. We get 32.634. And the units, all that's left, are meters. Now we also need 2 sig figs for this answer, because notice the numbers we used both had 2 sig figs. So 1, 2, look at the number next to it. In this case, that's going to round up to a 3. So our answer for distance would be 33 meters. Now I didn't explain this at the very beginning, but I want to point out why we looked at these specific equations. Because for this chapter, we have a ton of possible equations to choose from. And one of the first things you need to do when reading the word problem is figure out which area to look in for equations. So the reason I picked the 0 initial velocity equations is because when I read this question, it said, you get in a parked car. So since the car was parked, that means its initial velocity was 0, thus making me choose the 0 initial velocity equations. Let's look at another one. So in this word problem, we have a stomp rocket, and the stomp rocket boasts it can reach an altitude of 200 feet in 3.2 seconds. We're going to calculate acceleration and velocity. So if you don't know what a stomp rocket is, it's a child's toy or children's toy that has foam rockets that you place on a launcher. And how you launch them is you have this kind of an air pump that you jump on. And when you jump on the air pump, it shoots the air through and makes the rocket fly into the air. So it says that those rockets can go 200 feet. My kids have a stomp rocket and I've never seen it go that high. But that's beside the point. If it did go that high in that amount of time, let's see what the acceleration and the velocity would be of that rocket. So notice I still have my 0 initial velocity equations up. Why? Well, with what I just explained with a stomp rocket, you have a rocket sitting on a pedestal and it's at rest initially. So that means its initial velocity is 0. So that's why we're still applying this area of equations. All right, so we're going to do it systematically. And last time I didn't number them, so let me number them this time. So the first step is to write your knowns and unknowns. So my knowns, let's see. First number I see is 200 feet. So 200 feet, is that a distance, a velocity, an acceleration, or a time? It is a distance. Next, I see 3.2 s. That's seconds, so 3.2 seconds. That is a time, so I'm going to label that as t. Next are the unknowns, acceleration and velocity. So A question mark, V question mark. Once again, I'm solving for 2 different variables, so I'm going to need 2 different equations. Before I go looking for some equations, step number 2 is to convert if necessary. So, do I need to convert any of my knowns? Well, let's see. Distance. For this, we're looking at units. So distance, it was given to us in feet. Do we want distance in feet? We do not want distance in feet. We want it in meters because we need it in metric in order to use it in these equations. So I'm going to need a conversion factor, which you can find on your equation sheet. And that conversion factor is going between feet and meters. Let me write that here. So I have conversion factor. I get 1 foot is equal to 0.3048 meters. Do my little railroad tracks. What's going to go here? It's going to be the number I'm trying to convert. Then my conversion factor goes here, making sure I put the feet on the bottom, opposite sides of the horizontal line, so feet cancel. That'll put the other part of the conversion factor, the 0.3048, on the top. So I'm multiplying across and then dividing by what's on the bottom. In this case, it's just a 1, so I don't really need to divide. Anything divided by 1 is just itself. So doing that conversion, I get 60.96 meters. So I'm not taking into account significant figures. I'm just going to keep all the digits shown on my calculator because this is not my final answer. The more digits I keep, the more accurate my final answer will be. So I'm going to put that 60.96 here. Erase this to give myself some room. So step 2, done. I have converted. What is step 3? Find the appropriate equation and solve. So equation. Well, I said I'm going to have 2. So let's solve for acceleration first. So if I'm solving for acceleration, I'm going to look at all the equations with an a in it. And that's these bottom 3. So which one is going to help me solve? Well, let's see. I have distance and time. So the equations I'm going to look for are ones that have distance, time, and acceleration. Why do I not want ones with velocity? Because I don't know my velocity, and I can't have 2 unknowns in an equation. I could, but then it's going to get really difficult. So we're not going to do that. So any of these equations, and remember we're just looking at the bottom 3 because those are the only 3 with a in it. So which of them have distance, time, and acceleration? That would be just the last one. Okay, so we're going to use this equation, but notice we will have to rearrange it because we are trying to solve for acceleration. So we want to get the a by itself. So let me write this equation a little differently, and it's going to help us rearrange it easier. So all I did was I took this 1/2 and distributed it. So what that means is these equations are exactly the same. I just put the 2 in the denominator and the 1 is up here. I just didn't need to include it because anything times 1 is itself. Okay, so now I'm still doing the same thing, trying to get this a by itself. So to get a by itself, I need to move the 2 to the other side of the equation and the t squared to the other side of the equation. So how do I do that? Well, since I am dividing by 2 on this side, to get rid of it, I want to do the opposite operation. So right now I'm dividing by 2, so the opposite of division is multiplication. So if I multiply this side by 2, now I have 2 divided by 2. They're on opposite sides of that horizontal line. So by multiplying this side of the equation by 2, I just got rid of the 2. Whatever I do to one side of the equation, I have to do to the other. What that means is, since I decided to multiply by 2 on this side, I also need to multiply by 2 on the other side. So now I have 2d is equal to at squared. So I'm not quite done because I need to get a by itself still. Well, what am I doing with these variables? I'm taking a and I'm multiplying it by t squared. So if I want to get rid of the t squared, because that's my goal, is to move t squared to that side, so a is by itself, I want to do the opposite. So right now I'm multiplying. The opposite of multiplication is division. So I'm going to divide by t squared. Now t squared will cancel. So I got rid of it on that side. Since I divided by t squared on this side of the equation, I'm going to also divide by t squared on the other side of the equation. So now my equation becomes a all by itself is equal to 2d over t squared. So I'm going to erase this, put my equation up there, and then plug in my values. So using my rearranged equation, I am going to take 2 and multiply it by my distance in meters, so 60.96. And then I'm going to divide that by my time squared in seconds. So 2 times 60.96 divided by 3.2 squared. And I'm going to get an acceleration of 11.906, and the units are meters per second squared. Now, since this is one of my final answers, I do want to take into account sig figs, and you use the significant figures for the original numbers in the word problem. So 1, 2, 3, I have 4 sig figs here. The zeros count because there's a decimal, and I started counting at the 2. For time, I have just 2 sig figs. You always want to pick the smallest, so that means I want 2 sig figs in my answer. 1, 2, look at the number next to it. Is that 1 stay a 1 or round up? It will round up to 12. So my acceleration is 12 meters per second squared. Quite an acceleration for that stomp rocket. All right, so I've solved for one variable. Now I'm going to solve for the next variable, and that's the velocity. How fast is that stomp rocket going? So to do that, I want to look at the equations that have a v in it. So that would be these 3 equations. The average means average velocity, and it's not asking for average, it's asking for the velocity itself. In this case, it's actually final velocity. So it's going to be one of these 3. All right, well, what do I have? Let's see. I have acceleration, time, and distance. So really, either of these would work fine because I don't have average velocity, so it has to be one of these 2. But I'm going to pick this top one where v is equal to at, because that way I don't have to do any rearranging. I can just plug in and solve. I'm going to put my 12 meters per second squared here. That's my acceleration. And I'm going to multiply that by my time, which is 3.2 seconds. Now notice this seconds cancels out with one of these seconds. So my units will be meters per second, which is good because that's what we want our velocity in. So when I take 12 and multiply it by 3.2, I get 38.4. And I only want 2 sig figs, so I'm going to keep it at 38. So that stomp rocket is really flying, going fast, 38 meters per second. So that is how you do that guy. The next problem we're looking at is a moped, and it's moving at a velocity of 22 miles per hour. It then decelerates and eventually stops in a distance of 25 meters. We're going to calculate the time that is required for that moped to come to a stop and its deceleration. So a couple new things here. First off, notice the moped is initially moving, which means it has an initial velocity. So if it has an initial velocity, we can't use the zero initial velocity equations. We have to use the non-zero initial velocity equations. So let me change these and replace them with the non-zero initial velocity equations. This is the only equation that remains the same between the two. Get these in a different color so it's not melting in. So we have average velocity is 1/2 vi plus v. We have velocity is vi plus acceleration times time. Acceleration is equal to velocity minus initial velocity divided by time. And then distance will be initial velocity times time plus 1/2 at squared. Okay, so here's our new set of equations that we're going to use to solve this problem. We're using them because the object in question is initially moving, so it has an initial velocity. So now we're going to approach it systematically, where we start with the very first step, writing our knowns and unknowns. So way over in the corner, it tells us the initial velocity is 22 miles per hour. So notice now we have 3 different types of v values or v variables in the equations. We have v sub av, which is average velocity. We have v sub I, which is initial velocity. And then we just have plain old v. Now the plain old v would be final velocity is what that would stand for. So this 22 miles per hour, that's going to be our initial velocity because that is the speed or the velocity at which the moped was initially moving. All right, next I see 25 meters. It specifically tells us in the problem that that's a distance. If it didn't, I would know it's a distance based off of the units of meters. Now the unknowns, it wants us to calculate the time. And then it says deceleration. So that's something we haven't seen before. So what is deceleration? Well, deceleration is the same thing as acceleration. It's the slowing down version. So whenever you see deceleration, what you're trying to solve for is just the variable a. So wherever a is in these equations. We call it deceleration when the object is slowing down, and we call it acceleration when the object is speeding up. But we still calculate it the same, so these equations still apply. So once we have our knowns and unknowns, the next step is to convert if necessary. So do we have anything we need to convert? We have, let's see, 22 miles per hour. Do we want the velocity in miles per hour? No, we want it in meters per second. So we're going to be using the conversion factor. 1 mile per hour is equal to 0.447 meters per second. And you'll see we use this conversion a lot. You might even memorize it by the end of this class. So I'm going to go ahead and set up my railroad tracks. I'm going to start with 22 miles per hour, the number I'm trying to convert. Put the 1 mile per hour in the denominator. The 0.447 in the numerator. That way, miles per hour cancel. And I get my answer in meters per second, which is 9.834. Notice once again, I'm keeping all of the digits. I'm not rounding with sig figs because this isn't my final answer. So let me plug that guy up here. So this is the value that I want to use for my velocity in those equations. Okay. So next, let's look meters. Is meters the units we want for distance? Absolutely. So we know conversions needed there. So next, we can go ahead and find the equations that we need and solve. Once again, we have 2 variables, so we're going to need at least 2 equations. So let's see what we can do here. So for time, let's look if any of these equations will work for time. So I'm going to find equations with a t in it. All right, so if I use this equation, I'm going to need acceleration, which I don't have. So that one won't work. All right, let's look at this next one with time in it. I'm going to need acceleration. Dang it, I don't have acceleration. So that one won't work either. This one, once again, it has acceleration. So I can't use any of these equations because they have 2 unknown variables. So what do I do when that happens? Well, when that happens, I look at all the equations and I solve any of them that I can solve. Why? Because if I can add an extra variable, maybe then one of those will work. Distance I have. Time, nope, I don't have that. Average velocity? Nope, I don't have that, so I can't solve that one at all. What about this one? V average. Do I have the V average? I do not, so that's my unknown. Do I have initial velocity? I do. Do I have final velocity? Well, it's not written here, but maybe, let me reread and see. A moped moving at an initial velocity of 22 miles per hour. It decelerates and eventually stops. So what's my final velocity if that moped came to a stop? It's 0. So yes, I do have a V value. It just didn't explicitly tell me it was 0, but by saying it stopped, that tells me yes, it is. It's 0. So I can solve for my average velocity. So I'm going to do that first, because then maybe I can use another equation to get where I'm trying to be. So V average, 1/2, I'm going to use my initial velocity of 9.8 because we want to use the meter per second version, plus V, which is 0. 1/2 of 9.8 is 4.917. So I'm going to add this to my list of knowns. 4.917. Units are meters per second because it's still a velocity. All right, so I've added another one. Now let's approach it again. We're still trying to solve for time, so let's look at all the equations with time in it. We got the top one, so there's time, that's my unknown. Do I have distance? Yes, I do. Do I have average velocity? Yes, I just solved for it. So this one's gonna work. I need to rearrange the equation to solve for time, but I have all the information I need. So if I want to get time by itself, what this equation is doing is it's taking your average velocity and it's multiplying it by time. So what I want to do is the opposite of multiplication. The opposite of multiplication is division. So I'm going to divide by average velocity because that's the one I'm trying to get rid of. Whatever I do to one side of the equation, I have to do to the other. On the right side, it cancels, leaving me with t by itself. So I'm going to take distance and divide that by the average velocity to solve for time. So let's plug in my 25 meters, and then let's plug in my 4.917 meters per second. Meters and meters canceling, leaving me with an answer in seconds. So when I divide that out, I get 5.0844 seconds. All right? Now we got to look for sig figs because this is one of our final answers. So I have in my initial velocity 2 sig figs because that's one of our original numbers. My other original number, distance, also has 2 sig figs. So that means I just want 2 sig figs in my answer. So it's going to be 5.1 seconds. So it took 5.1 seconds for that moped to come to a stop. So I solved for one variable, let's solve for another. The other variable I need to solve for is acceleration. That means we want to look at all the equations that have an A in it. I'm going to look at this one first because if I have the information I need, this will be the easiest one to solve because I won't have to rearrange it since its A is equal to. Do I have final velocity? Yes, I do. It's 0. Do I have initial velocity? Yes, I do. They gave it to me and I converted it. Do I have time? Yes, that's what I just solved for. So I'm going to go ahead and pick this guy as my equation and I'm going to plug in the appropriate information. The final velocity was 0. The initial velocity is 9.834. And then my time is 5.1. So notice we're going to get a negative acceleration. So why is it negative? Because we're slowing down. So when we're slowing down, acceleration is referred to as deceleration, and the value is going to be negative. When we're speeding up, acceleration is just called acceleration, and the value will be positive. So we get negative 1.928 meters per second squared. We said 2 sig figs, so it would just be negative 1.9. So that's going to stay a 9. All right, so I think we've solved for every possible variable we can in that one. So those are our examples for zero initial velocity and non-zero initial velocity.